Okay, so I'd like to go over some of Chapter 24, which is on optical instruments. The goal here is to understand some common optical instruments and their limitations. So here are some telescopes on the top of Mauna Kea in Hawaii that are used for focusing light from distant stars and galaxies. So when you have two lenses used in combination, or multiple lenses used in combination, there's just one new rule you have to use, which is that the image for one lens becomes the object for the subsequent lens. So for example, here's an object and it's held out beyond the focal length of lens 1, where the focal length of lens 1 is f1. So if you set s1 as being the distance of the object from lens 1, then you can use the thin lens equation to find s1 prime, which is the image distance from lens 1 of this object. And so an image forms here. And that means that these rays are focused to this real image. But if there's no viewing screen there, then those rays will start to diverge again. And so now this image can be treated as an object for lens 2. So I call it S2 without the prime is the object distance of this new object for lens 2. And we can use the thin lens equation for lens 2 to find S2 prime, the image distance for this lens 2. And that's essentially how you use multiple lenses. And there's some examples of that in the textbook that I'd like you to look over. So, a camera. A camera takes a picture by using a lens, a converging lens, to form a real upside-down image in a light-tight box upon a light-sensitive detector. There's usually an aperture which allows only light through a certain part of the lens. So when cameras focus on objects that are more than about 10 focal lengths away, so that's greater than about 20 centimeters for a typical digital camera, then we would say that this object is at infinity, so that the S prime for the lens is about equal to f. Okay, so 1 over infinity is 0, so the thin lens equation boils down to s prime equals f. And in that case, the lateral magnification, or the ratio of the image size to the object size, is negative, meaning it's upside down. S prime over s becomes negative f over s. And since the focal length is usually much less than the object distance, then this magnification is much less than 1. Okay, but more importantly, the size of the image on the detector is directly proportional to the focal length of the lens f. That's going to be important in a minute. So the other thing we have to worry about is the aperture. So in a real camera, there is a hole with an adjustable diameter called an aperture. And the diameter of the aperture is called d. So how much light is gathered by a lens or by a camera is specified by its f number. So the f number is defined as the ratio of the focal length of the lens to the diameter of the aperture. And so it turns out that the bigger the area of the aperture, the more light is allowed into the camera. And also, the bigger the focal length of the camera, the bigger the image. So the area of the image on the detector gets greater by the square of the focal length. So the intensity on the detector is proportional to basically the area of the aperture divided by the area of the size of images on the detector. So it's d squared over f squared. Turns out to be proportional to 1 over the f number squared. And that's why we have focal length and f number usually stamped somewhere on a camera. So in a real camera with a zoom lens, we have multiple lenses all acting together to create an effective lens with some effective focal length. And as you change the distance between all these intermediate lenses, you change the different focal lengths to be, for this camera, anywhere between 5.8 millimeters up to 23.2 millimeters. And that's a factor of 4 difference, so this is a 4 times zoom lens. You can change the size of images on the detector by a factor of 4 just by changing the zoom. And then the second numbers here, it says 2.6 to 5.5, that's the range of f numbers. So the f2.6 corresponds to the 5.8 millimeter focal length, and the f5.5 corresponds to the 23.2 millimeter focal length. So the detector is called a CCD, or a charge-coupled device is what that stands for. Most people just call it the chip. And what the chip has is many, many pixels, so millions of little pixels, and each pixel is covered by either a red or a green or a blue filter, so it's sensitive to only one of these 3 colors. And there's so many pixels, and they're so small that the picture looks smooth. Okay, but as you can see, if you zoom in too much on a picture, on any photograph, you will start to see the individual pixels, these little squares. Okay, so next I want to talk about vision, and in particular focus on, or concentrate on the human eye. So the human eye is, the eyeball is roughly spherical. It's about 2.4 centimeters in diameter, and it contains a cornea and a lens. The lens isn't really labeled here, but it's just behind the pupil. And these are the main refractive elements that tend to focus light. And the eyeball is filled with liquid, or a jelly-like fluid, called the aqueous humor in front of the lens and the vitreous humor here behind the lens. And the index of refraction of the aqueous and vitreous humor is about 1.34. It's similar to water. And the index of refraction of the lens is a little higher, 1.44. The pupil is a hole in the iris, which can automatically open and close to control the light intensity, how much light comes in through the eye. But the focal length f is fixed to be about this 2.4 centimeters, the diameter of the eyeball. But by changing the diameter of the pupil, you can actually vary the f number from f3 when you're using your largest diameter and maybe night vision, all the way up to f16 when you have the smallest little diameter, like if you're outside on a sunny day. So this range of f numbers is very similar to a camera. The eye's detector, the retina, contains, instead of pixels, it contains light-sensitive cells called cones. And there's actually 3 kinds of cones, the B cones, G cones, and R cones. And shown in this graph is the relative sensitivity of these cones versus wavelength. So you can see they're sensitive to different parts of the spectrum. And that's how we have color vision. The relative responses of these types of cones gets interpreted by our brains as being various colors, red, green, or blue. You can have mixtures, so red and blue together, but not much green would look purple to our eyes. If you had all 3 being stimulated, then you'd see white light. And other animals have different kinds of cells in their retinas, so they would see different wavelengths that perhaps we could not see. So how does let's talk about focusing. So the eye focuses on different distance objects by changing the focal length of the lens. And the way that happens is the lens is actually malleable. And it's surrounded by muscles which can squish the lens and decrease the lens's radius of curvature to make it more curvy, and if it's pushing in on the lens, and thus decreasing its focal length. So that allows objects at a particular distance to have their image focused right on the retina. So it's only going to look focused to our eyes if the image happens to land right on the retina. And the ciliary muscles in our eye automatically adjust the shape of the lens to make that happen. So the furthest distance at which a relaxed eye can focus is called the far point, and that would normally be out at infinity. And by infinity, I mean an object that's any further than about maybe 3 or 4 meters away. We would call that infinity, so that rays are coming in essentially parallel, and then the lens is relaxed and the rays focus onto the retina. The closest distance at which an eye can focus comfortably is called the near point. And for most people, the near point is 25 centimeters. And this, when you're looking at an object 25 centimeters away, that's when the ciliary muscles are contracted to cause the lens to be squished maximally and have its smallest focal length, so that, again, rays diverging out from here converge to be on the retina. So there's a whole field of optometry, which I'll go over a little bit, which is dealing with corrective lenses. Okay, so corrective lenses are prescribed not by their focal lengths, like every lens has a focal length, but it also has a power, lens power. And lens power is defined as 1 over the focal length. So if the focal length is measured in meters, the lens power is measured in 1 over meters, or meters to the -1. And optometrists have a special name for that unit called the diopter. So 1 diopter is defined as 1 inverse meter. So for example, if you have a lens with a focal length of ½ a meter, then the power is 1 over 0.5 is 2 diopters. So there's 2 main kinds of vision problems you can have, hyperopia and myopia. So hyperopia is called farsightedness. So if you're farsighted, you can see faraway objects, but you can't focus easily on objects that are too close. And so what this means is that your near point, instead of being 25 centimeters, is greater than 25 centimeters. That's called hyperopia. And the cause of hyperopia is usually that your eyeball is a little too short. So your retina should be back here, but in fact it's closer. And so instead of all these rays from a near object at 25 centimeters being focused onto a point in the retina, it's focused to a blurry spot, stimulating many cells and just making the image as in total look blurry. To correct hyperopia, you can use a positive lens. So if you have a near object and a very weak but positive lens, this will form a virtual image behind the object, or further from the eye than the object. And it's set up so that the virtual image is further away from the eye than the person's actual near point. And that's what the eye focuses on, is this virtual image. Myopia, sometimes called nearsightedness, is when, even when the lens is completely relaxed, you cannot see distant objects. So what happens is, if you have an object that's too far away, then it'll focus down to a spot that's before the retina, and then the rays again diverge and once again form a blurry spot. So here's something from a very distant object. There's a blurry spot instead of one little point of light. And so the image, if you're looking at stars or something like that, all the stars look blurry. To correct myopia, you add a lens with a negative refractive power. And what that does is, if you have a very distant object, it'll form, like parallel rays for example, it'll form a virtual image which is closer than the person's far point. Okay? And then that's what you focus on, is this virtual image, for example, of a star. Okay, I want to talk about magnification. So if you want to magnify an object, you can do it without any optics at all. Just get closer. So for example, here's a car, and here is the same car, but it looks much bigger, and it's easier to see details in this car in this image than in this image, because it looks like about 3 times bigger. What's happened here? The car hasn't gotten any bigger, the car has gotten closer, so the angular size of the object as we see it is now larger. So how that works is, here's two arrows. The red arrow is the same size as the green arrow, but the angular size of the red arrow is greater than the angular size of the green arrow. Theta 2 is greater than theta 1, and so what that means is that the image on the retina of the red arrow is greater than the image of the green arrow. So you can magnify things without any optics at all. Just put them closer and closer to your eye. So if you wanted to look at a cell or something, you could just place it right in front of your eyeball, right? No, you can't keep increasing an object's angular size because it's difficult to focus on objects if they're closer than about 25 centimeters. That's a very practical limit, isn't it? You just can't focus on something. So the maximum angular size of an object viewable by your unaided eye is called theta near point. It's this object size, h, divided by 25 centimeters. h over 25 centimeters. So a magnifier is like a magnifying glass. So that's one single converging lens that's used to look at a nearby object. What we do is we will tend to take a magnifying glass and set it up so that the object's distance from the lens is less than the focal length, so that we see an upright, enlarged virtual image that's further away and easy for our eyes to focus on. So when you use a magnifying glass or magnifier, you see a virtual image that has angular size of h over s, where s is the object distance. And if we place that image at infinity, then s is around f, so that's actually h over f, the focal length. And we call magnification as being the ratio of the apparent size of the object when using the lens divided by the apparent size when it's, or the angular size when it's just at your near point, which remember was theta near point was h over 25. So if you solve this all out, you get the magnification is 25 centimeters divided by f for a simple magnifier. A microscope, which I'm going to show in the next slide, has a two-step magnification process. So you have a specimen. It gets placed on the stage of the microscope beneath the objective lens. The objective lens is a converging lens with a relatively short focal length. And then so that creates a real image, and the real image is further enlarged by the eyepiece. So there's an objective and there's an eyepiece. And so here's the eyepiece, here's the objective lens. In this real microscope, there's actually a prism that bends the light path so that the eyepiece is at a more comfortable angle. There's a stage which can be moved up and down to help focusing. There's an illuminator with some lights to keep things bright enough. And there's a focus knob which moves the stage up and down. But looking at the light path, here's the object, some small little thing, and here's the objective lens. And the focal length of the objective lens is less, just a little less than the distance between the object and the objective, so that you form a real image. And the real image is up here in the tube. The tube has some length between the objective and the eyepiece of L, and then the eyepiece is used as a magnifier to view this this real image. Okay, and we usually set the eyepiece so that we're looking at using our relaxed eye to look at this image out at infinity. So the magnification of the objective is s prime over s. Turns out to be negative L over the focal length of the objective, and we know that the magnification of the eyepiece is 25 over the focal length of the eyepiece. So combining these two magnifications by multiplying them, we end up with the total angular magnification of a microscope. L over f objective times 25 over fi. And there's a negative sign to remind you that the image is upside down. And as it turns out, most biological microscopes you can buy have standardized tube lengths of 160 millimeters. So sometimes you see this as 160 millimeters over the objective focal length times 25 centimeters over the eyepiece focal length. So next, telescopes. So microscopes look at things that are very close, telescopes look at things that are very far. So a simple telescope collects parallel rays from a very distant object and forms a real inverted image, which is then viewed with an eyepiece. So again, the eyepiece functions as a simple magnifier to look at the real image, which is created by the objective lens. In a telescope, in a simple telescope, the viewer looks at an inverted image, and the magnification, which is the angular size from the eyepiece divided by the angular size, I guess, with no telescope at all, sometimes called theta objective, or the angular size as viewed by the objective lens. This is equal to just the ratio of the objective lens focal length divided by the eyepiece focal length. So how that looks, here is some parallel rays from a very distant object, maybe a star, and they're coming in at an angle to the optic axis of theta objective. And then this objective is a converging lens which forms a real image over here at f objective, if this is off at infinity. And then over here we have an eyepiece which acts as a magnifier to look at this this real image. And we set the eyepiece to look at it out at infinity. So if you want a large light gathering power, you need a large diameter objective lens. But large lenses are difficult to actually produce and to hold up and support when you're pointing a telescope in different parts of the sky. So many people use reflecting telescopes where you have a mirror that's mounted on some big metal disc so that you can point it around, it doesn't sag, and the mirror is concave to focus light down onto, again, a real image, which is then again viewed by an eyepiece. So glass lenses have dispersion. That means that the index of refraction can vary slightly with wavelength, and what that does is it means that the focal length actually depends slightly on wavelength. So these purple lines are meant to represent white light. So white rays come out, and then that white light is split out into a rainbow. Here's red, orange, yellow, green, blue, violet, which is where the different focal crisp focuses will be. And that's called chromatic aberration. So you can never get a perfectly focused image for white light. Spherical aberration is when you grind lenses that are spherical surfaces. They don't quite focus at the ideal point. The actual surface should be a little more complicated, and so and it isn't. So that means that rays that are coming sort of further out away from the optic axis end up getting focused at a different point than rays that are closer to the optic axis. So you end up with a kind of, again, a blurry point over here. That's called spherical aberration. And you can correct for aberration sometimes by using multiple lenses that sometimes use different materials or have different shapes. And so in most optical instruments, we'll use many lenses, or multiple lenses, not just two, perhaps maybe as many as 5. And sometimes the reason for that is to correct for various spherical or chromatic aberration so that all the rays end up at the same focus. So lastly, we didn't do chapter 22, but I quickly want to touch on diffraction. So what happens if you have, even for the best lens, it still does not focus all the rays down to a perfect point. Instead, it makes a spot of width W min. The minimum spot size or diameter of a spot is 2 times f times theta 1. So it's 2.44 times lambda times f over d. So for a point source, like a very, very, very distant star, you'll get a spot of diameter which is related to the wavelength, the focal length of the system, and inversely proportional to d, the diameter of the lens. So a bigger diameter telescope sometimes can be used to create crisper images with smaller spot sizes. And why you want small spot sizes is so that you can resolve 2 point sources. So the closest 2 point sources can be on the sky and still be resolved is called theta min, and that's called the angular resolution of the lens, and it comes as 1.22 times lambda over d, where lambda is the wavelength of the light and d is the diameter of the telescope. And that's called the angular resolution of this telescope.